Section 10.2, Summing an Infinite Series. The vocabulary here is very important, so let's recall the difference between a sequence, a finite series, and an infinite series. We're really recalling the definition of a sequence here, and we're defining what we mean by a finite and an infinite series here. So a sequence is just a sub n equals a1, a2, a3, dot, dot, dot. We'll consider this pattern repeating forever. So this is just an ordered list of numbers. On the other hand, we could take that list of numbers and we could add them together and say maybe add the first capital N terms, A1 plus A2 plus, we'll keep going until we get to A sub capital N. Maybe capital N is 3 or 7 or 15. It's some fixed number. This would be a finite series because we're adding, finite because there's only finitely many terms. Notice this stops after finitely many terms. We're adding the terms of the sequence. A sequence is just a list. You're not performing any operation on the terms in the list, but a series is adding the terms in a sequence. And then an infinite series takes that one step further, and it just adds infinitely many of these terms. So A1 plus A2 plus A3 plus A4, dot, dot, dot. It continues on forever. Now this we know how to handle. This is obviously just adding up finitely many terms. There's no issue here. We call this a finite series. The real issue here is what happens when you have infinitely many terms. How do you sum infinitely many terms? Well, let's back off a little bit before we answer that, and let's give the following definition. Let a sub n be a given sequence, so we know this sequence. The nth partial sum of that sequence, we'll denote that by s sub capital N, so think of capital N as a fixed number. It's given by S sub n is all we're going to do, we'll explain it before we write it down, is we're just going to go to the sequence a sub n, and we're going to sum from the first term up to the capital nth term. So we're going to take a1 plus a2 plus a3 plus dot, 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 all the way up to a sub n, whatever the n is. So this is just the sum of the terms of an up through the nth term. This is why it's called a partial sum, because if this is an infinite sequence, we're not summing all the terms, we're just summing part of them. It's the nth partial sum because we're summing up through the nth one. Okay, so for example, if our sequence is the standard A1, A2, A3, dot, 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 then S1 would just be A1, it's the sum up through the first term. S2 is A1 plus A2, it's the sum up through the second term. S3 is the sum of up through the third term, A1 plus A2 plus A3. S10 would be the sum of A1 plus A2 plus keep going all the way up to A10. And as this gets longer and longer to write down, we could have done this here or here or here. As this gets longer and longer to write down, we can more succinctly and compactly write this using summation notation. So this is just the sum from little n equals 1 to 10 of a sub n. This would be what s sub 10 is. It's very important that you notice the distinction between the little n's and the big n's here. They are playing completely different roles. Finally, s sub big N is a1 plus a2 all the way down plus an, and we would write this as the sum from n equals 1 to big N of a sub n. So note that s sub capital N itself is a sequence. It's a sequence of sums, because look, this is a list of numbers. It just so happens that the way you construct that list is by summing things. So S sub n, ironically, it's the nth partial sum, but it generates a sequence of those partial sums as capital N varies. Let's look at a concrete example. Let's let an equal 3 over 2 to the n, where n goes from 1, 2, 3, dot, 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 and continues forever. Then S sub 1, that's just the first partial sum. It would be the sum up through, from the first term up through, you stop at the first term. So this is sort of trivial. You would just get a1. In this case, a1 is 3 over 2 to the 1. S2, the second partial sum, would be summing up through the second term in the sequence. So we would get a1 plus a2. This would just be a1, we said was 3 halves, and a2 would be 3 over 2 squared. That's just a number. We'll just leave it in this form. S3 would be a1 plus a2 plus a3, which is 3 halves plus 3 over 2 squared plus 3 over 2 cubed. Notice all we're doing is every time we advance, we're just adding one more term to our sequence of sums. If you want to, we could write this in summation form. S10, we'll skip ahead, is A1 plus A2 plus A3 plus dot dot dot, all the way up to A10. So that would look like this. And if we wrote it in summation form, because sometimes maybe this is easier to spot, or maybe we're going to put this in a calculator or a computer algebra system, this is a very succinct way to write things down. Notice that all that is changing once we write it in the sigma notation is we're just changing this upper limit, capital N. S sub 15, the 15th partial sum, is just the sum of up through the 15th term in the sequence. And that gives you this, which we can rewrite in summation notation as this. Now, these would be tedious numbers to compute, but we could compute them. I'm just going to put them into a calculator or computer and compute them, because that's not what my main point is. My main point is to see what's happening to the sequence of partial sums as capital N gets larger and larger. So now I'm going to write down and plot not just little n and a sub little n, but big N and s sub big N. So this is a real paradigm shift. Here I'm writing down the n's. I'm going ahead and letting a computer calculate these numbers for us that I've highlighted in yellow and finding out what the s sub n is for each n. And if you do that, it looks like these numbers are settling down. It looks like they're settling down to 3. I'm not claiming that this is a proof. This is just numerical evidence. And graphically, we can see that happen also. This is a graph of n on this axis and capital N on this axis and s sub capital N on this axis. We can see that what's happening is we're accumulating these terms here in the s sub n in the partial sum, and it looks like that graphically that they're settling down. It's very, very important. We must always maintain a clear distinction between the concept of a sequence, between the concept of its associated nth partial sum of the sequence, and the concept of an infinite series. If you can keep these three things straight, it will really help your understanding throughout Chapter 10. A sequence is just an ordered list of numbers. The nth partial sum is where you sum up through the capital Nth term in the sequence. You can write it in summation notation like this. And then an infinite series is when you don't sum all just through the capital Nth term, but you sum all the infinitely many terms, and we write it like this. This is no problem, but the question is, how do we sum these infinitely many terms in this series? That leads to this definition. An infinite series converges to the sum S if the sequence of its partial sums, so if we start with this series, from that series we're going to generate an associated sequence of partial sums like we did here. If you go up in this example, we had a sequence. From that sequence, or you could even think we had a series if you think of we were summing these. From that, we generated a sequence of partial sums. We calculated those sequence of partial sums, and now what the definition is going to say is we'll say that the infinite series converges if and only if the sequence of partial sums has a limit, if it converges. So let's take a look at that definition again. So an infinite series converges to a sum S if the sequence of its partial sums converges to S. So we want to calculate the S sub capital N's. We want to let capital N go to infinity. And if that limit exists, we'll call it S. Then that number, whatever it is what we will call the sum of this infinite series. Now, if the limit does not exist, we say that the infinite series diverges. If the limit is infinite, which is another way for it not to exist, we say that the infinite series diverges, or maybe a little more precisely, it diverges to infinity. We don't necessarily split those hairs. Divergence is totally fine. So it seems like in example 1 above that the limit of the partial sums, S sub n, was 3. That's not a proof. We'll be able to verify this a little bit later. And so we would say that the sum of the infinite series, 3 over 2 to the n, is 3. Now, although we will develop faster and more efficient ways to determine convergence or divergence of an infinite series, and when it converges, perhaps what the sum to which it converges is, the definition above is the foundation for all of those concepts. It's very important that we have a good understanding of this definition. So make sure that you concentrate on this definition and understand that the sum of an infinite series is just defined to be the limit of the sequence of partial sums. Either that limit of the sequence of partial sums exists as a finite number, in which case the infinite series converges, or it doesn't exist as a finite number, in which case we say that the infinite series diverges. Okay, let's now look, we've talked about in the last section about geometric sequences. Let's talk about geometric series, which you can probably guess is just the series version or the summation version of a geometric sequence. So a geometric series is just any series involving a geometric sequence. Now, it could look like this. It could be an infinite geometric series. It could look like this. Notice these start at two different places, but they still have the same core component of the c, r to the n, the geometric sequence. Or it could be a finite geometric series. And now these are completely different than these. We need to keep them in separate categories, but we would call all of these geometric series. Okay, so we're really interested in, just like we were with geometric sequences, when do they converge and when do they diverge? For what values of the geometric ratio r do they converge and do they diverge? We want to play that same game with a geometric series. And this is going to be very, very fundamental all throughout chapter 10. So consider the geometric series. Notice this starts at 0. This is very, very important. The template here is that our geometric series always starts at 0. And so that means its first term will be c. If it doesn't start at 0, then you need to do some kind of algebraic manipulation of the form of your series to turn it into a form that does start at 0. So it starts at 0, and then it has, as its argument here, it has the standard geometric sequence. And we'll take this with a geometric ratio that's not 1. We already said that if it is 1, that we already talked about what happened with the geometric sequence. But the reason we don't really need to talk about this when r is 1, because just look at this. If r is 1, we're just summing up infinitely many copies of the constant c. And as long as c is not 0, we're adding up infinitely many constants. There's no way that that can converge. It's going to diverge, either to positive infinity or negative infinity. Okay? So, if we go back to this, the theorem just says that if you have a geometric series with a geometric ratio that's not 1, and you look at the nth partial sum, which we could string it out and make it look like this, then that will come out to, this is the thrust of the theorem, that sum comes out to be c times 1 minus r to the n plus 1, those parentheses are important, all over 1 minus r. So notice that this is for the nth partial sum, so this is for a finite geometric series. For a finite geometric series, when you're only summing up through the nth term, this is the formula. Now, where does this formula come from? Well, what we're going to do, the idea is actually pretty simple. It's an algebra proof. So the S sub n is this by definition. So if we start with this, and we take our geometric ratio, which we would know, we multiply this equation by r, then we would get this. If we take this line minus this line, if you notice, you take this line and you subtract this line, everything here is going to cancel. I'll even highlight it and show you here. Everything here is going to cancel, 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 cancel. Everything's going to cancel. The only things that are going to be left are the c and the c times r to the n plus 1. And we're subtracting them, so we get this right here. And so that's what this difference is. Now, when you look at the left-hand side, we can just factor out an S sub n and divide both sides by 1 minus r, because we know that r is not 1, so we're not dividing by 0. And so we get the formula that was claimed up here. It's actually a very straightforward algebra proof. On the other hand, what if we're summing, and I'll give you an example before we move on. So if we take a look at this example, suppose we were summing this geometric series, and we were summing from n equals 0 to 6. Now first, we need to rearrange that and make sure we can spot that it's a geometric series, and it is a finite geometric series. We can see it doesn't go to infinity. It's a finite geometric series. It's the sixth partial sum, if you will. Here we'll just factor out the 3. We'll write the 2 to the n in the denominator. We'll write it as a 1/2 to the n, so this matches our template, and these are equivalent. We now spot this as a finite geometric series. The c is 3, the geometric ratio is 1/2, and the n is 6. So we just apply this finite geometric series formula with a C of 3, an R of 1/2, and an N of 6. And when the algebra dust settles here, the arithmetic dust settles here, we get that this finite geometric series has a sum of about 5.95. You can check that. Okay, on the other hand, what if we want to sum an infinite geometric series? Maybe something like this. Well, let's look at our theorem. It says, well, let's suppose that our constant is not 0. It would not be interesting if our C was 0. Let's take our geometric ratio R to have an absolute value that's less than 1. So in other words, our R is between -1 and 1, strictly between -1 and 1. Then, if you take the sum of the geometric series that starts at 0, this is very important. For this formula to hold, it has to be a geometric series that starts at 0. If you write out the terms, you get this, and there are infinitely many of them. But this infinite geometric series will sum to be the number C over 1 minus R, as long as the geometric ratio has an absolute value that's less than 1. On the other hand, if the absolute value of the geometric ratio is greater than or equal to 1, the geometric series, this infinite geometric series, is going to diverge. This is very, very important to realize that geometric series converge when their geometric ratio has an absolute value of less than 1, and they diverge when they have a geometric ratio that has an absolute value that's greater than or equal to 1. This is sort of reminiscent of p integrals, where r equals 1 here is exactly the critical case that separates convergence from divergence. Okay? R equals 1 and r equals -1. So the proof here just says, well, if r is, let's separate the case when r is equal to 1. Well, if r is equal to 1, just like we said before, we're going to be summing infinitely many copies of C, so that's going to diverge. On the other hand, if r is not equal to 1, we can go back and use our finite geometric formula that we had up here, equation 3. We can use this to write down the nth partial sum. Let's come down here. And so what we want to do is we want to take the limit of the sequence of partial sums. We know what that is. When you only have capital N of them, it comes out to be this from our formula 3 above. Let's actually take the limit as n goes to infinity. And as n goes to the infinity, what we want to do is distribute this C. And then we want to split this up into C times 1 over 1 minus r, which is here, minus C times r to the n plus 1 all over 1 minus r, which is here. And now this stuff is independent of capital N, so we can apply the limit only to the part that has capital N, and this is what we get here. Now, if you notice, this is just a constant. This is something that's independent of capital N, so it has no bearing, the limit has no bearing on it. So we really just need to calculate the limit of this piece right here. And notice, stare at this. If absolute value of r is less than 1, then you have a number whose magnitude is, whose absolute value is between -1, absolute value is less than 1, its magnitude is between -1 and 1, and, or the value of r is between -1 and 1. And so you're raising it to a higher and higher power, so this term's going to 0, precisely when the absolute value of r is less than 1. So that limit is going to be 0, and when that limit is 0, this term goes away, and we're left with this, which is exactly what we had in equation 4. And on the other hand, if the absolute value of r is greater than or equal to 1, well, now we have a number here whose absolute value in magnitude, this is growing as n goes to infinity. The absolute value here is greater than 1, so this limit does not exist, and that will cause this limit to not exist, which says in that case, the geometric series diverges when the geometric ratio has an absolute value that's greater than or equal to 1. As an example of that, suppose we were looking at the infinite geometric series, the summation, n equals 0 to infinity of 3 over 2 to the n. Let's first rewrite it like we did before to make sure that it matches our template. And so we see that our C is 3. We see that r is 1/2. So we just apply, here our geometric ratio is 1/2, which has an absolute value is less than 1. So we know we're going to get convergence, and we can just apply this formula. Remember, you have to get convergence in order to apply this formula. So we get C over 1 minus our r, which is just 6. And so when you add infinitely many of these geometric sequence terms, it comes out to be 6. On the other hand, if you had this geometric series, notice it does match our template. Notice this started at 0. It was very important that it completely matches our template. Our C here is 2. Our R is 5/4, which in absolute value is greater than 1. And so we don't even need to compute anything. This is a geometric series with a geometric ratio greater than 1. It does not converge. The series diverges. Okay, a couple of other things we need to enter into the official record. Again, linearity of infinite series. It basically says that if you have convergent series, infinite series, and you want to do the sum of an plus bn, that we can rewrite that as the sum of the ans plus the sum of the bn's. If you have the sum of the ans minus bn's, you can do the sum of the ans minus the sum of the bn's. And if you have the sum of a constant times an, you can do the constant times the sum of the an's. So this just tells us that we have the green light to use several of the algebraic properties that we've used in a variety of situations in the past. Now that can be computationally very helpful for us. For example, here, if you had the sum from n equals 0 to infinity of 2 plus 3 to the n over 5 to the n, if you stare at that, that's not a geometric series as it stands. But if we use our linearity that we just said and we split this into the sum from n equals 0 to infinity of 2 over 5 to the n plus the sum of 3 to the n over 5 to the n, that as long as these converge, this is a legitimate decomposition. And now we can rewrite this as a 2 times 1/5 to the n. We can write this one as a 3 over 5 to the n. If you stare at this, this is a geometric series with C, it does start at 0, This is a geometric series with C equals 2, R is 1/5. The geometric ratio has an absolute value less than 1, so this converges, and it converges to C over 1 minus your geometric ratio. Similarly, this has a C of 1, an R of 3/5. The absolute value is less than 1, so it converges, and therefore this series converges to C over 1 minus R. This comes out to 5/2, this comes out to 5/2, and so we just get 5 as the sum. Okay, the last thing that we need in this section is what our textbook calls the nth term divergence test. A lot of books call this the test for divergence, and I probably will refer to it as the test for divergence because that's the way that I've learned it and also the way that I've taught it out of many other books. And it simply says this: if you have a sequence that when you take the limit of the an's, it does not go to 0, then there's no possible way that the series, the summation of the an's, can converge. In other words, if the an's don't go to 0 as n goes to infinity, then the sum of the an's must diverge. So this is a test for divergence. It's to just rule out before you expend any energy trying to determine convergence. If you just look at it and the an's don't go to 0, then you know that the series must diverge. Okay? So, for example, does the sum from n equals 1 to infinity of n over 3n plus 1 converge or diverge? Now, this is not a geometric series. We don't have many tools at our disposal right now. We have a well-cataloged set of geometric series about their convergence and divergence, and we have some theorems in our toolbox from this section, but we don't know anything about this sequence yet, or this series yet, I'm sorry. Well, if we take the an's, the sequence, the an's are n over 3n plus 1. If we take the limit of the an's, that's the limit of the n over the 3n plus 1's. This, again, is an infinity over infinity indeterminate form, so by L'Hopital's rule, this goes to 1/3. That's not 0. So notice what the test for divergence said. If the an's don't go to 0, as n goes to infinity, then the sum of the an's must diverge. So notice the an's did not go to 0, so the series must diverge. Don't expend any more energy trying to figure anything out about that. You know that the series diverges. Now you have to be very careful. The test for divergence says that if the an's don't go to 0, then the sum of the an's cannot converge. But just because the an's do go to 0, that does not mean it is not sufficient to ensure that the sum of the an's converges. You have to be careful. So just like with improper integrals, where if you remember when we did p integrals, the integrand had to go, improper integrals of the first kind, the p integral, the integrand, the p function had to go to 0 fast enough in order for the improper integral to converge. So we have a similar situation here. If the ANs don't go to 0, then there's no way the sum of the ANs can converge. On the other hand, if the ANs do go to 0, that's not sufficient to guarantee that the ANs converge. They have to go to 0 fast enough to guarantee convergence. Now, that's not something that we're going to fully explore right here in this section, but it is something that we will unlock in the future sections, so just stay tuned for that.